First of all, I want to remind you that in this chapter, we are repeating and relearning everything that we have learned for two random variables, just we are extending it to a random vector. So the concepts are very similar. So let us discuss about conditional densities. So if you have like a number of random variables, let's say x1, x2, let's say xk plus 1, and let's say xn. And then, so I have n random variables. I divide them in two groups. This is one group, this is another group. Suppose that I know the values of the first group and I want to find the distribution of the second group. So the conditional distribution of the second group, given or assuming the values of the first group is known, can be calculated using this notation. This is notation and then is equal to the joint distribution of all of them. So this is the joint distribution of all random variables divided by the marginal distribution of the condition. So from the joint distribution, you can integrate with respect to, let's say, the groups that is you're trying to find. Then you can find this one and then do this definition. So obviously, from these general definition, you can prove this lemma, which is called chain rule, because in some application, first you have the distribution of first one, then the second one given the first one, and then the third one given the first two, and then the last one given the previous one. So this chain rule is good because let's say at time n you want to process this one. This is the first time, this is second time, and so on. So recursively, you will get more and more of the distribution. So this guy is the distribution of the first one. Product of these two is fx1 and x2, and then once you add, you get the distribution of the next one as well, as so on. So using this chain rule, you can easily prove this theorem, which is like if you have any joint n joint random variable, and then suppose that you have the joint distribution, the joint CDF or PDF and so on, you can easily calculate the CDF of the first one, CDF of the second one given the first one, and so on. Now, if I define a random variable y1, because usually here I don't have a random variable, but if I substitute random variable x1 with the distribution, so remember that x1 has a distribution of fx1 of x. If I generate x1 using this distribution, and if I use the same CDF to define this one, we have seen in one of the earlier chapter that this has a uniform distribution over the interval of 0, 1. Now, if you generate a random variable x2 and you put x1 and x2 here, we will easily prove that this also has a uniform distribution in the interval of 0, 1, etc. And then this also has a uniform distribution between 0 and 1. Not only that, we will right now prove that these random variables are independent. So in other words, y1 to yn are having identical distribution, independent distribution, and all uniformly distributed over the interval of 0, 1. So this is a very simple theorem. So the interesting part of this theorem is that from the same equation, so you could, the inverse part of this theorem is important because you could generate uniformly distributed random variables independently. So you could, in a generation process, so you could generate, the application is that you could generate y1, y2, yn as n independent random variables uniformly distributed between 0 and 1, and then apply the inverse of this function, fx1 inverse of this function, in order to calculate x1. Now, you can get x1 and this y2, give it to the second function, and then apply this inverse. So f x2 given x1, because this is a function, inverse in order to calculate x2, etc. And then the theorem says that the joint distribution of this one is the given distribution that you started. So this theorem is important in the sense that it gives you one way to generate any arbitrary joint distributions. Now let's try to prove it. So first we denote y as a random vector, as a column random vector. This transpose means that y is equal to y1, y2 to yn. And now we want to find the joint distribution of this random vector. So we want to prove that these random variables are independent and have identically uniform distribution over 0, 1. So this theorem is used, can be used. I'm not suggesting that this is a good way to generate arbitrary distribution, but this is one of the ways, one of the easy ways to generate a random vector with a given joint distribution. Because if you have the joint distribution of, let's say, fx1, x2, xn, x1, x2, xn, so from these functions, you can calculate this one, calculate this one, calculate this one, and then you can generate these guys uniform distribution, and then you will be able to find a way to generate a random vector x, x1 to xn, which has this distribution. So the proof is very easy. So the first part is that we have to solve it. So from this equation, we have to solve this set equation. So replace this one, x1, x2, etc. And then we try to solve it. So from here, then we have to calculate the solution. So we see that because this CDF is a function which has to increasing, because we said that these functions are the continuous. So all of these functions are continuous. So for a given y, let's say 1, you have a unique solution. So all of them, they have a unique solution. So yi's, if they are above 1 or below 0, there is no solution. So only when yi's are between 0, 1, you have a solution, and the solutions are calculated. The inverse of this one, inverse of this one, and so on. So you can get the solutions. And then nowhere else there is a solution. So the joint PDF is 0, where either of yi's is not in the interval 0, 1. And when all of them are in the interval of 0, 1, a Jacobian, which is equal to derivative of this one with respect to x1, derivative of this with respect to, if you calculate the derivative, it is upper diagonal, so I don't care about these guys. And then this becomes product of diagonal elements. So if you calculate these guys, this guy will become, derivative of this will become PDF of x1, conditional PDF of these conditional. So then this result will become just these guys. And then what you can do is that you see that the Jacobian will become the joint PDF. And then the PDF of y is equal to this guy divided by Jacobian. This guy divided by itself is equal to 1, when all yi should be equal to in this interval. So in other words, these random variables, they are independent and have identical uniform distribution over this interval. So you may generate these guys as independently generated random variables uniformly between 0, 1, and then apply these inverse of the CDF, the conditional inverse CDFs, to find this one. So this function gives you this, because if you calculate y1 gives you x1, and then you plug this x1 here, and then you apply y2 here, which is generated by you, and then gives you x2, then these guys, you have it from the previous one, and then you give this new uniform random variable here, it gives you xn. So these outputs, set of outputs x1 to xn, they will have the desired distribution that you want.